Join the conversation.
You're with Cape Talk.
Yeah, boy, yes. It is Friday. It is just after 9:39. My name is Clarence. I'm with you through 12 o'clock. It's Views News. And it's going to be a whole lot of fun. Lots of different stuff we're chatting about today. This is the opportunity to have that question that's been bugging you for all of your life answered. The question that keeps you awake at night. And the Naked Scientist joins us. Dr. Chris Smith is with us. And we're going to go straight to the phone. Margaret is there in Goodwood. Margaret, you have a question for the Naked Scientist. Go ahead.
What I want to know is when we spray for flies or bugs, we can smell the aerosol. Now, my question is, what damage does the molecules or the poison do to us?
Good morning, Margaret. These things work is that they contain a substance, usually, which inhibits a nerve transmitter in the insect. When nerves talk to muscles, they use a nerve transmitter, and in the case of most animals, it's acetylcholine. And the way that this is released is in response to an impulse coming down the nerve. This pumps out some acetylcholine, and this activates the muscle. And the action is terminated by an enzyme called a cholinesterase, which breaks apart the molecule and stops the signalling. So if you give a drug, which in the case of these insecticides is an anticholinesterase, it's a chemical that blocks up that enzyme, basically you can no longer terminate the transmission of information from the nerves into the muscles, and so the muscles continue to contract all the time. And this is what causes the terminal effect for the fly. Thankfully, the amount that a fly needs to kill it compared to us is very low, and they have only one form of this cholinesterase, whereas we have other forms, which means that we're much less susceptible to the effect of the drug. So it doesn't harm us because it's specific for the fly, and in that way you're achieving a selective toxicity. That's not to say, though, that at huge doses there might not be some kind of impact on us. And I spoke to some researchers in Western Australia who are doing very sensitive analytical techniques a few years ago, and they were able to show that even at really low concentrations, you can still see effects of some of these molecules on our physiology, although the effect is so tiny that with small exposures that you get from spraying a fly, you really don't see any kind of consequence. But the cumulative effect can't be ignored, which is if you did this day in, day out over a lifetime, there may well be some kind of impact, not necessarily just on that part of your nervous system, but in some off-target way. So this is why it's really important that we're careful about the chemicals that we produce, use, distribute, and then put into the environment, because at very low concentrations, they may not have an obvious demonstrable effect on us directly, but if you then look for long enough and hard enough, you may find there are effects, and there probably are. So the bottom line is that at the levels we use these things, we think they're safe, and we don't think that they affect us significantly, but we always keep an open mind and we always keep looking, just in case.
And then, Dr. Smith, somebody wants to know, explain what muscle memory is and how long it takes to occur. Samantha with that question.
Good morning, Samantha. There's a couple of things that we're referring to here. Part of muscle memory is training. And when you have done exercise or you've used a muscle and you've stimulated it, you make it grow a bit. So part of when we go down the gym and bulk up and get strong and become fitter is that we're using muscles and making muscles develop more. They lay down more proteins to make contraction happen and therefore produce more force, and they also change their biochemistry to augment their ability to get oxygen from blood, and also they change their biochemistry in such a way that they're better at metabolizing energy with oxygen so that they don't produce waste products that make the muscles fatigue. So that's part and parcel of training a muscle, but you're probably referring to the fact that if I put in front of you a piece of paper and I said, I want you to write on this piece of paper a map of where all the keys on a computer keyboard are from memory, you'd probably say, I have no idea. And then you might start pretending to type some words with your fingers and realise, in fact, you do know where all of the words are on the computer keyboard, but they're in movement patterns rather than as a discrete memory of the Q is at the top left, the W is next to it, the E is next to that, the R, the T, the Y, U, I, O, P across the top line, for example. You would do that because you have muscle memory. And this is because some aspects of our memory are sequences of movements which are programmed into a part of the brain called the cerebellum, which cerebellum is the small brain. And if you imagine a person with their cut in half down the midline and you looked from the side, at the back of the brain, roughly, if you were to clasp your hands behind the back of your head, your palms would be pointing towards your cerebellum. There is a small structure, it's about fist-sized at the back of your head, and this is very much uniquely bound up with how we make movements and execute them at the right rate. And our muscle memory and a lot of our motor learning goes on there, and in another region of the brain where we execute movements called the striatum, which is very intensively connected and intensely and richly connected to the cerebellum. So we have circuits in our brains which are dedicated specifically to sequences of movements and therefore execution of muscle movements, and we tend to ascribe muscle memory, remembering how to ride a bike, how to type words and patterns of movements, and how to speak actually, to those sorts of centres in the brain. So there's sorts of muscle memory which are training your muscles, getting them to develop biochemically so they're stronger, and then how to make sequences of movements and patterns of movements at the right way, right time in order to produce outcomes.
It's our time with the Naked Scientist through till 10 o'clock. You're welcome to put a question to Dr. Chris Smith. Les in Citrusdale called that number, and he's worried about that 1% that goes unimpacted. Go ahead, Les.
I'm a she, not a he.
Gotcha.
Okay. I'm wondering for many, many years, especially since the beginning of the pandemic, why every bottle of, bleach, Dettol, Domestos, etc., says it kills 99.9% of all germs and viruses. And I've really been wondering, what is this 0.1 germ virus that we can't kill?
Yeah, it wasn't just since the pandemic. That's always been there. And this is the biochemical / microbiological equivalent of arse covering. Because they can't say with certainty that this kills everything, because it won't. If you take some bleach and you swab down a surface, then there might be a micron of that surface that you miss, and in there might be a trillion bacteria. Well, there wouldn't be a trillion because they take up too much space, but there'd be quite a few million microbes potentially in that bit of space, and they wouldn't die. Therefore, when you say kills all these germs, well, you don't know that for sure. So by saying 99.9%, they're as sure as damn it, and sure as they can be, that it's going to get rid of most stuff, but it might miss the odd one. Most things that we are aware of, there are very few infectious entities that will not be destroyed by bleach. It's a strongly oxidizing agent, and by bleach we're referring to hypochlorite, sodium hypochlorite solution usually, although there are other ways to bleach things with hydrogen peroxide, for example. They both work as bleaches and they both oxidize living things, tissues, to the point where they are destroyed. But that doesn't mean that there aren't some infectious entities that will potentially persist despite bleach. Prions that cause CJD, for example, are resistant to bleach, and they're an infectious entity. So although they are careful in couching their language, we're pretty sure that bleach is a very good way to sterilise the surface, but because medico-legally you can't say 100%, because we never say never in medicine, that's why they cover their backside in that way with that language.
On the topic of bleach, a question in about rainwater. Andre says he's been collecting rainwater in his tanks for a while, but he's worried about the purity of the rainwater. And he says his neighbor suggested using bleach to clean it. How much bleach is required to make water safe?
We have to be very careful because, of course, there may be other additives in bleach. If you just go and dump toilet cleaner in your fresh water supply, then there may be other things in there, anionic surfactants and so on, detergents, things to give the bleach a characteristic so that when you clean a sink or a toilet, it sticks to the surface for long enough for the descaling properties that may also be in there to work, and the bleach to have good contact with the surface, get underneath the biofilm of the bugs that are growing on your bog to make sure that they're all deactivated. So it's not straightforward to say, well, I just put this stuff in and everything will be fine. It's a reasonable thing to say that rainwater caught from a roof is not clean. And the reason for that it's not clean is because birds sit and poo on your roof, other things come down and land on the roof, all this washes off of the roof, down your gutters and into your rainwater tank. And it's full of organic matter, which will include bacteria and fungi and other bits and pieces, and a source of food for those bacteria and fungi. And what do microbes need to flourish? They need food, which includes phosphorus, which is in bird poo, and the sources of nitrogen, which are in bird poo, and sugars and other things which are coming in from the environment, moisture and a bit of warmth. So yes, you will grow microbes in your water tank. There are some ways around this. One way is to minimise the amount of muck that goes in your water tank in the first place, and this is called a clean catch system. And the way this works is that you have a way of getting rid of the first load of water that comes off the roof before you start filling your tank up. And one way to do that is you have a big vertical tube with a ball inside it which floats, and you have a slight leaky connection at the bottom of that pipe. So as the water first washes off the roof, it goes down into this vertical pipe and fills it up, rising the ball to the surface, which then plugs the input to that pipe, and the water then goes across the top of the big vertical pipe and then goes down into your tank. The rationale behind this is all the muck goes in the vertical pipe to start with, and you can then empty that later, and then the clean catch stuff goes across and down into your tanks. Should you add chemicals to your tanks? Yes, there are things that you can add to these sorts of supplies. People who go on camping holidays have Steri-tabs. People who go on caravanning and motorhome holidays have sterilizer systems that you can flush through your system with. Those can come with clear instructions as to how much you should put in order to sterilise a known quantity of water, and they don't leave residues or contain substances which may be harmful to our health. So be very careful about what you add to your water, especially if it's going to be in there for a while. Check that it's compatible with your water system. You don't want to rot your pipes out because you put something in that's a bit too aggressive, and minimise the amount of bacterial food you add to the tank in the first place with the sort of strategy that I've suggested. And this will help to keep down the level of microbes, although what's in there is going to be probably of little harm and impact to human health, because rainwater is pretty clean, and what birds have got is much of a threat to us, but you don't want to take the risk.
Let's go to a physics question. Looks like a gravity question. Naked scientist, do you agree that apparent weightlessness experienced by the occupants of the International Space Station is because the ISS is perpetually free-falling downwards faster and faster towards the Earth, but maintaining a constant altitude above the curved surface of the Earth? That is the question. Dr. Chris Smith.
The answer is yes, absolutely. That's completely right. The way to think about this is, and Isaac Newton was the person who of physics fame from Cambridge who had this insight hundreds of years ago, and he did a simple thought experiment to consider what is an orbit, and therefore what is weightlessness. And his thought experiment was, if I fire a gun and the cannonball comes out of the cannon and I don't fire it very hard, it will come out of the cannon. It will start travelling along, but at the same time gravity is pulling it downwards. So at some point it will hit the ground, because although it's going along, the gravitational pull has drawn it towards the ground and eventually it lands. So if you fire the gun a bit harder, it will then travel a bit further, the cannonball, before the ground gets in the way because it hits the ground. So if you then fire the gun really hard, because the Earth is a curved surface, as the cannonball goes along and falls down a bit because of gravity, the Earth has curved at the same rate along a bit as well, and you can achieve a speed where the ball is going along and down, but the Earth is going along and down at the same rate because it's curved, and so the ball will never hit the ground, and that is an orbit. So a person who's inside the International Space Station is falling all the time towards the Earth like that cannonball, but because they're missing the Earth, because it's curved downwards and along out of the way at the same rate that they're falling, they're continuously falling towards the Earth, but they're missing it because the Earth is curved out of the way. And that's how an orbit works for an astronaut, a space station, or a satellite. So that person is continuously accelerating. Why are they accelerating? Because they're going in a circle, and an acceleration is a change in velocity, which is a speed with a direction added to it. So therefore they're continuously changing their velocity, therefore they're continuously accelerating, but they are going in a circle because that gravitational force is pulling them towards the Earth but they're continuously missing the Earth at the same time.
Okay, a question about a Cape cobra. Dr. Chris, I'm a snake fan, and last year I came across a cobra on my property. I have it in a tank, but my partner is freaked out and insisting I get rid of it. Will it remember how to hunt and survive, seeing that I've been feeding it? Arthur, you naughty boy.
Oh, I don't know the answer to this because I've never kept snakes. I do know a man who does, and if he's listening, he knows who I am as well. He's a wonderful South African wildlife guy, and supplied a number of David Attenborough documentaries with the animals that they've studied. So hello to you. But the answer to this is that some animals are very simple creatures and they hunt in a way that is behaviourally programmed into their nervous system. So they almost certainly would be okay, and they almost certainly would not become victim of something, fall victim to something, because most things would stay out of their way. But some creatures with more complicated behaviours, with social behaviours, and I'm thinking higher creatures, things like primates, for example, you have to be very careful under these circumstances. Some birds, if they're a social species and they learn off each other and they have no idea how to form a relationship with each other, they would struggle. But simpler creatures, reptiles included, I think would probably do okay in the wild. But if anyone knows better, then please do let me know and put me on the right track.
Dr. Smith, why do some people sweat excessively and others not?
Well, first of all, what's sweating and why do we do it? Well, we sweat because we need to maintain a steady body temperature, because we are homeothermic, warm-blooded, to put it in common parlance. And the way that we maintain a steady body temperature is by either producing more heat to keep us warm when we're cold, and we do that by shivering, altering our metabolic rate, or putting clothes on or going into a warm space, or we lose heat when we're too hot by diverting blood towards the skin surface, taking off layers of clothes, opening windows, going outside, drinking a cold drink, and magically sweating. And sweating is where you activate a branch of your nervous system called the sympathetic nervous system, and there are a specific class of nerve fibers which happen completely under automatic control. It's like autopilot for temperature control. You don't have to think about this, but you activate nerves called pseudomotor nerves, which supply sweat glands in the skin, and these are eccrine sweat glands, which, when you activate them with this nerve impulse, takes the fluid from the blood that's supplying them, the plasma, and filters it through the cells in the gland into a duct system, which produces a salty, watery liquid, which then oozes out onto the skin surface and evaporates, taking with it the latent heat of evaporation, so that you take out some extra heat as the water evaporates, helping to cool you down. So some people sweat because they have trained, and people who are athletes who do a lot of exercise under heat stress conditions can increase their density of sweat glands and the efficiency of their sweat glands, so they make more sweat. So that's one reason. Another reason is that some people naturally have the ability to sweat more than others. Some people naturally just sweat less, and that's part of human variation. And in some people, there are problems with the nervous system, so that they excessively activate their sweat glands, sometimes under inappropriate conditions, and they have a condition called hyperhidrosis. And they'll often complain they have clammy, damp hands. If they're doing anything, that they'll leave a trail of dampness behind, and they find it very embarrassing, because if you want to shake someone's hand and then they get hold of a wet lettuce, it's not a terribly good social interaction, and they find they have to continuously wipe their hands on things, and it's very distracting. So there are ways to stop that by interrupting the nerve flow, which can be done in various ways, into those sweat glands. So the simple answer is you sweat a lot because you can, you sweat because you've trained to sweat more, or you sweat less because that's natural variation. And some people have a nerve issue, which means they excessively sweat, and that can be treated by giving drugs like Botox to interrupt the nerve signals, and that can make them sweat less for a while.
Dr. Chris Smith, we're going to have to wrap it up there, unfortunately. The Naked Scientist. Thank you, Dr. Chris Smith, for that interaction. Some of your questions we were able to get to. Others will hold over. News up next.